is real and the output is also real. We'll be starting off again with a set of examples. Now the feature, you have a single feature x or the attribute x, and what you're predicting is y. Both of these are now real quantities, as you can see, right? The first question for you, this is based on pretty much what we've been seeing thus far. If you have to learn a decision tree with depth 0, then what is the estimated prediction of y hat based on this particular example? It will be 1. Why is that the case? So the output will now be predicted to be 1 because that's the mean across the data set, and we're not splitting on any attribute, right? The prediction would be something like the following. Now, what this is saying is that irrespective of x, your y hat of x is always 1, right? Not a pretty good model at this point. Now let's think about, and you have only one attribute to split, by the way. Okay, how do you think a depth 1 tree will look like? You have only one attribute to split. So it has to be based on some x1 greater than equal to. Choose one.
X equal to 3.5.
Okay, so x equal to 3.5.
Or we x equal to 2.5.
Okay, so can anyone tell me some good candidate split points? X equal to 2.5. Okay, anyone? Any other point? 4.5, or let's say between 4.5 and 5. Why is 3.5 not a good split? So the question is, why is it not a good split? Because then the error on prediction would be, or there will be more standard deviation amongst the partitions. So we continue with the same set of motivation. A depth 1 tree turns out to be something like the following. You split x on less than or equal to 2.5. If it is true versus false, if x is less than 2.5, then you can very clearly make a good prediction where y is 0, right? And what is the standard deviation of variance for this particular subset? When x is less than or equal to 2.5, the standard deviation of variance is 0 because you're not deviating about the predicted value, which is 0. Whereas on the other side also, you can see that the standard deviation is slightly reduced. Okay, what if we have to make another split? We have made one split on 2.5. If we have to create a decision tree with depth of 2, it will look something like the following. x0 less than or equal to 2.5, you get the first split. Then if it is true, then we predict the value to be 0. If it is not true, then the value is 1.5. Let's go back to that. Perfect. So if x is greater than or equal to 2.5, then the value that we're predicting is the mean across all of the other samples. So that turns out to be 1.5. And if we do a depth of 2, then for x0 less than or equal to 0.5, 4.5, you then predict the value to be 1 or 2. It would look something like the following. If x less than 2.5, then this is the value 0, you predict 0. If x greater than 2.5, you can then again split the tree into x is less than or equal to 4.5 or greater than 4.5. If x between 2.5 and 4.5 prediction is 1 and otherwise prediction is 2. So the goal, what we're trying to do here is to find some fine split points which again partition the space into different regions. And for simplicity, let's assume that we have a single attribute which we're trying to split on, x equal to s. So let's say that for x less than s1, we have region R1, and for x greater than or equal to s, we have a region R2, right? So the only main question which remains at this point is, how do you choose the value s? How did you choose the value S for this example? Minimum variance amongst the samples on the split. But in this case, it was fairly easy to to observe and choose S. Could you come up with a more principled way of choosing S? The most reduction in variance. Okay, and which are the points? So will you choose those points on a real line, or are those split points small number of finite points which exist on which are somewhat close to related to these different points? Okay, which so could you come up with something simple algorithm?
Taking midpoints of 2 points.
Okay, excellent. So that's the whole algorithm. I just walk over that. First, let's again clarify. We have two regions. X is less than S, given as R1, and X greater than or equal to S, given as R2. Let's calculate 2 quantities, C1 and C2. C1 is the mean of the yi's of all the samples where the X belongs to region 1, right? And similarly, C2 is the mean of all yi's where X belongs to region 2. If we go back, let's say if we choose 2.5 as a split. So this particular, if we choose 2.5 as the region, then the blue region shown is R1 and the red region shown is R2. What is the mean of the values of yi's for this region R1? That is 0. And the mean of the values for the other region is 1.5, right? So you have now calculated C1 and C2 to be 0 and 1.5 for this particular split F. And what you're trying to maximize is to find an S which leads to the minimum deviation in this particular region of interest. So intuitively you'll want, once you've done a split, let's say you have split into blue and red, you'll want a minimum amount of deviation across both of these splits for all the points that exist within the split. Right? So if you had chosen somewhere here, then the mean would have been around 0.5 and the mean for this would have been around, say, between 1 and 2. The deviation of points within this blue region and the red region would have been 9. So that is the objective that we're trying to minimize. So minimize for all I, for all the examples, yi minus c1, and this is for the region where xi belongs to region 1. Similarly, for all the xi's belonging to region 2, you subtract the mean, you calculate the square of the mean from all the possible examples. Right? So in some sense, it's telling you the variance about the point, about the mean chosen for these separate subsets. Right? Fairly simple algorithm. And then our objective is to minimize this expression and find out a value of x. To keep things simple, one such way of finding an s, which we have also discussed thus far, we first sort the data points in increasing order of x, which was also done in the visualization that we had. We already had points sorted out in x. And that is why visualization was easy, or finding out the split point was easy. And then you evaluate the loss function for all possible s, which are at the midpoints of two adjacent points, right? And then you select the s with the minimum loss. For example, we could have picked s as between 1 and 2, or we could have also picked s to be less than 1. Let's say if s is less than 1, or s could be 1.5, it could be between 2 and 3, between 3 and 4, between 4 and 5, between 5 and 6. It turns out to be the best one is between 2 and 3, and then if you want to split further, between 4 and 5. Okay, so this is a brain teaser. Now, imagine if you have y equal to sine of x, where x is varying from 0 to 2 pi. Can you draw a decision tree for that? So you have so the real input that is given to you is x, the real output given to you is sine of x. You have to draw a division tree, which means that you will keep on splitting the value attribute s or the attribute x into different, like x is less than 0, x is less than 1, x is less than 2. And then for all of those levels, you have a continuous line. Right? So this, if you have not seen thus far, so for real input and real output, the division tree that we learn is piecewise constant, right? Across the region. So for the blue region, the prediction is a piecewise constant, is a constant. For the green region and for the red region, again is a constant. And you have, this is piecewise constant. This is exactly what will happen if you also try to learn a precision tree on the sinusoid. But it would be fun if you can think for a couple of minutes and try to draw. You don't need to gap it. Just try to see how sine is your process. Imagine whatsoever number of levels you want to use. Okay, just looking at this visualization, what kind of a split point do you think would be appropriate? Will it be at pi or will it be at pi by 2? Pi is at pi. I would hope to see. So let's see what was computed. Yes, what is computed is fairly close to pi. So it's not exactly pi because this was from 0 to 7 and not 2 pi. It turns out to be x is less than equal to 3.033. The decision tree at this point looks fairly stupid, it's fairly rudimentary. It will predict the value of, it predicts the value of 0.657 for all values less than 3.03 and it predicts the value of some minus 0.44 for all the values otherwise. If we were looking at a perfectly symmetrical system and we were splitting at the midpoint, then the value would be equal and opposite. If we increase the number of levels, we will see something like the following. These are the kind of split points that we have. And interestingly, you will see that the troughs and the crest, they have a broader region where we don't have any splits. Any idea why? Yes. Excellent. Because if you look at the top, so it's a slowly declining function. Right? The slope is gradually reducing over time. So there are more changes happening in the before pi by 2 than they're happening closer to pi by 2. So we'll now summarize and finish the discussion on decision trees, and we'll quickly go on to bias, variance, and cross validation. We have seen that interpretability is an important goal of machine learning. Decision trees are very useful machine learning algorithms for interpretability. And we've also seen that learning optimal trees is hard. So we thus come up with some greedy approximations or some greedy algorithms to learn decision trees. The greedy sense is that we look at statistical measures which give us the biggest estimated performance gain and not the actual performance gain. And the estimated performance gain that we use is criteria like information gain or reduction in entropy. But one of the problems is that they can overfit easily. We haven't yet discussed what is overfitting. And sometimes it can be empirically not as powerful as other methods. Specifically for things like this, like you could have perfectly well fitted a polynomial function or a sinusoid, right, and figure out the parameters. Let's now start the other discussion. Okay, a quick exercise for all of you. We have two different classes, blue and yellow. What would be the decision boundary of a decision tree classifier? And let me turn on the lights. What do you think would be a decision tree learned for this data? So you need to just tell me the split points. First would be x. Okay, so let's move forward. How many things first would be on x1? How many things first would be on x2? Let's see what is actually being learned. Okay, the first one is on x1, and that's primarily because you see more yellow points over there and more blue points over there. So this seems like a fairly natural split point. Here there are although a couple of points which are going to be misclassified, specifically x1 equal to x2 equal to 2, and x1 equal to 6 and x2 equal to 2. These are going to be misclassified in this particular decision tree. We learn something like the following. This is depth 1. Let's make a decision tree without any limits on the depth. Right? So you can keep on going and you can keep on partitioning this space, and you'll end up with something like the following. So you see a red region within a blue region, and you see a blue region within a red region. Now it could very well be the case that these two particular points which are some observational noises, or they would not normally occur in the general samples, but they just happen to occur in a specific data set. So what we've done is something which is not ideal. We've tried to, we've tried very hard to look at all the artifacts and to look at all the possible data points and try to maximize the accuracy on this set, right? So we have seen that if we learn deeper trees, we'll end up with very complex decision boundaries. In fact, in the previous discussion when we were talking about decision trees and we went up to depth equal to 10, we saw very, very complicated decision trees. But more complex decision boundaries often lead to poor generalization. Can anyone explain why? Or what do we mean by this? So can anyone remind me the goal that we started with the previous lecture? So we wanted to learn a classifier which, or a regressor or machine learning algorithm, which generalizes to unseen samples. And we said that all of the trained samples and the test samples are coming from some hidden true distribution, right? So we want to maximize the performance on the generalization performance or on unseen samples, which are again coming from the population. But what we have thus far done is to create very complex algorithms and decision boundaries to only get the maximum accuracy for the trained set. Right? And it could very well be the case that generally this is the kind of data that exists. So imagine this: the right hand side, the test set, being the the true distribution, or if you were to draw a lot of samples, this is the kind of distribution that you'll get. So the decision boundaries should ideally have been as two squares, right? But what we'll end up learning is something different, right? So we'll now look at two extreme variants of decision trees to try and understand where machine learning can often go wrong, or where are the kind of errors in machine learning coming from. The first is called underfitting or bias, and let's look at this particular tree now. We said that a perfect classifier would have been a square, right? To separate out the blue dots from the yellow dots. But let's say that we wanted to be very specific, or we had a very biased perception that a simple tree like this would work, right? So we said that this tree is only being split on x2 greater than 5.5 and x2 greater than 1.5. So only two level tree. Will this lead to accurate results? Would any tree of depth 2 lead to accurate results? Why or why not? So does everyone agree that this is the depth 2, 3? You have done one split on x2 greater than 5.5 and the other split on x2 greater than 2.5.
Because we need 4 splits to get the accurate.
You need 4 splits to get the square, right? So what is happening here is we are ending up misclassifying all of these examples which are to the left, all the blue examples which are to the left of x1 equal to 1.5, and all the blue examples which are to the right of 5.5. We end up misclassifying, right? So we want to get them correctly, but we're not able to do that. The reason is we have a very high bias or a very incorrect assumption about the fact that the classifier is only a level 2, right? So that is why this problem is known as high bias. It's a biased incorrect information. This is also called underfitting. So underfitting means we have not done a very good job at learning the classifier, which works well even for the training data set, right? We're not even talking about generalization accuracy or generalization performance for now. This decision tree will not work well even for the training set, as we discussed, ignoring 2 specific regions of the square or 2 specific boundaries of the square, right? So underfitting is one problem. How can you remedy underfitting? You can increase the complexity, right? You can increase the complexity of the classifier. Let's say that you end up increasing the complexity of the classifier without any limits, right? Can you end up with a classifier something like the following? So now this particular classifier is trying to accurately predict all the points in the training set, right? It's already obtained this particular square, which is of our interest, but it is also trying to see how to accurately fit the 2 blue points in the middle of the yellow region, which would again have been noise, best be ignored, but because we had no depth limits, we ended up learning a very complicated classifier. This particular problem is called overfitting. You have fitted to the training set and you've gone beyond the limits to try to do a very good job at training. But this will lead to very poor generalization performance, right? You'll see, so in the generalization, in the test set, you'll see a lot of yellow points in there, right? Which will now be misclassified, right? So you have, in order to fit very well to the training set, you have ended up doing a bad job of generalization, which is called overfitting. This problem is also called high variance. Any idea why? Without looking at the slide, where it is mentioned. So again, variance is related to varying a lot. So what will happen is if we were to perturb the training set even a little with such a complex decision tree or without node limits, depth limits, we'll end up learning something very different. Let's look at an example. Let's say that we have 2 different train data sets, both of which have the same general pattern. If you were to learn a perfect decision tree, the decision tree learned would be the same across both of these examples. Do you agree? It would only be a square. But now we see that there are 2 blue dots in dataset 1 and 2, which is slightly perturbed. And if you look at the decision tree learned for both of these, can you see how different these 2 are? So very complicated and very different decision trees. So what this is telling us is that there is a lot of variance in the learned classifier. And if you were to perturb even a little, you'll end up with a totally different classifier. And this variance is occurred because you were trying to accurately predict the sort of anomalies or you were trying to do a very, very good job at predicting or classifying for the claims. So overfitting is synonymous with high variance. Underfitting is synonymous with a high bias. And now let's try to do both of them in a common way. And as we've been discussing, this would be a good fit, where we learned a square as the decision boundaries. So another way to discuss the bias, variance, and the trade-off is to look at the accuracy curves for both the train set and the test set. Right? We have the depth of the classifier of the decision tree on the x-axis and the accuracy on the y-axis. Okay, so why is initially the accuracy very poor? Let's for now look at only the train curves. Why is the orange train curve telling us low accuracy when the depth is low? Because we've made a very incorrect biased assumption about the depth of the tree or the classifier being 1, which will lead to now poor train errors or poor train accuracy, which will indeed also lead to poor test accuracies, right? Because it's not a square that you've constructed. But we can observe that as the depth is increasing, the train accuracy keeps on improving. It seems to be a monotonically increasing function. It's not decreasing in it. Why do you think that happens? Why does the train accuracy keep on improving with increase in depth? So train accuracy could have been bad. Let's say if this was a learned classifier, the train accuracy would be not perfect because you're misclassifying two examples, right? But if you were to go without any depth, you could have learned this classifier. So if you increase the depth, you would have increased the train accuracy. But we also see that if the depth increases, the test accuracy improves, but only to a specific point, right? Only to a certain depth will it improve. And after that, at very high depth, the test accuracy is not good. It can also reduce. It will very likely reduce after a point. That is the point of overfitting. Let's look into this again in a more detail. When depth is low, this region is known as the underfitting region because there is very high bias. You have made a very incorrect assumption. And the train accuracy as well as the test accuracy will be very poor. At this point, I think it's more important to just look at the train accuracy. Test accuracy we should naturally follow to be poor if the train accuracy is poor. And in some sense, the model is too simple, which is the bias which we have introduced. At the other end, the model is very, very complex. It is now trying to figure out all the nuances of the training data set. And thus it has a higher amount of variance also. And this specific region is known as the overfitting region or the high variance region. Right? So typically what you'll see is that after a certain point, the certain complexity, the test accuracy keeps on decreasing, whereas the train accuracy keeps on improving. So the point where the test accuracy starts to fall down, that is the point you ideally want to choose. Right? And that is the depth you ideally want to choose for your classifier. And this region in between is what I was talking about. In this region you have reasonably good train and test accuracy, especially towards the latter half of the region. So now one question that how do you choose this particular depth? We have thus far spoken that you want to choose a certain depth, but empirically, how do you choose this for machine learning experiments? Sorry. Okay. So one suggestion is to see when both the train accuracy and the test accuracy is increasing. Do you agree with this? So we've thus far not discussed validation, but can we use test accuracy? When the test accuracy is above train accuracy is not necessarily a good point. You can see that initially also at some point. So test accuracy is above train accuracy even for depth equal to 2. But you don't stop there. So even before that, should you be looking at test accuracy to decide the depth of the tree? Yes or no? How many think yes? So this is one of the biggest mistakes in a lot of machine learning papers. This is called optimizing for the test set. Right? If you see many machine learning papers will say that we got 95% accuracy. What they end up doing is they choose the parameters which gives the best performance on the test set. But is the test set observable to us? Alright, it's coming from the real world. The assumption is that you've never seen the test set. Thus, you can never optimize a set of parameters on the test set, which is the other set now left to you, the train set. But we see that if you optimize for the train set, you will end up with a very complicated tree, or very complicated decision, or complicated machine learning algorithm. So this seems to be problematic. You can't use the test set. Using the train set is also not good because you'll end up optimizing for the train set. So we need something in between. And that procedure is called cross-validation. So previously, and this is the flow that we've been seeing thus far, which is partly problematic. We said that you train on the train set, you learn a model, and at this point of time, you were choosing the set of parameters or parameters like the depth, technically the hyperparameters, which are giving you the best performance on the train set, right? And then once you've chosen the model, you use the test data and the model to predict. You get the predicted labels or predicted real predictions. And from the actual labels and the predicted labels, then you can calculate the accuracy or whatever technique you're looking at. But what we want to do is optimize for the best depth, which will give us the best generalization performance or the best performance on the test set, right? So we need some proxy for the test set, right? So we said that the test set is unseen set. Train set you can keep on optimizing and get infinitely complex decision trees or classifiers. We need a proxy for the test set, which means we need a set which is unseen to the training process, right? So that's the key intuition behind what is known as the validation set. What we now do is to divide the entire data set into a train set, a validation set, and a test set. You do the training on the train set. You learn different classifiers. Let's say you learn a classifier with depth equal to 1, a tree with depth equal to 2, depth equal to 3, and so on and so forth. Now, it's obvious that with the depth equal to say 10 or 15 or 20, that tree will be performing best for the train data, right? But will that tree be performing the best for an unseen validation data? That is probably not known, and that is also what we're trying to figure, right? So validation set, we use as a proxy. It's an unseen set. We calculate the accuracy for all of these different depth trees on the validation set, whichever gives us the best accuracy. For example, from this set of observation, it appears that depth equal to 2 is better than depth equal to 1 or 3. We choose depth equal to 2 or 3. We relearn the model on the train and the validation with depth equal to 2, and then we predict on the test data. So if this is not clear, please let me know. This is one of the most fundamental things which will keep on repeating throughout the course.
Sure. It's like we are trying to find a depth which will give accuracy, good accuracy for both training and test data.
Yeah.
So it's like test data is used in the training process.
No, test data is never used in the training process. You have, so ideally what we do is that test data is unseen to you, right? So imagine that test data is given to you later. It's not a part of your data set, or it's not a part of when you're training, right? That's the ideal case. So think of it as you've done some, so we were talking about the grocery example, right? Tomatoes. So there the test set would come when, so there is a production system, and then new tomatoes are coming. You have not seen these tomatoes earlier. But what typically ends up happening is that we have data sets like Iris data set that you'll be using for the assignment, the real world and the real estate data set. There the observations are all given to you, right? So you just have a single data set. So there you divide the data set into a train set and a test set. You don't see the test set, you see only the train set, learn a classifier, and predict on the test set, right? But what we're saying is that if we just optimize the train set, then that is problematic. That can lead to overly complicated models. Thus, you need another proxy for an unseen data set, which is now the validation set, right? So ideally what you end up doing is you split the train set that you have into the actual train on which you train and a validation set. So train set is given to you, you split it into the set you train on and the set you validate on.
So validation set is a subset of trains.
It's a subset of, so again there are variants of this. Sometimes you get some data sets where you have a separate train validated test. But typically think of it as you are given some training data. Right? Now using this training data itself, you have to figure out the best model. You divide the training data itself into train and validation. That's what is typically being done. It's a proxy for the test set, but it's a part of your training data. It's unseen for the model while you're training, but you then get the predictions on the validation set, and then you say that the set of hyperparameters like depth of the model, which gives us the best performance, is the one which I'll end up using. Right? So do you see how this is a proxy for the performance that you get on the test set? This is not going to be fully, really good proxy at times, but it's a reasonably good proxy. Okay, so another question you might ask at this point is that you given the data set like the INS data set or the real estate prediction data set. Now let's say that consists of 100 examples, right? So how do you divide them into train and test? Or train and test and validate? So one of the goals is that you want to test on all the samples, right? Why do you want to do that? So will you be more confident if your data set gives good accuracy on 30 samples or if it gives good accuracy on 100 samples? 100 samples. Another interesting thing would be that there is some bias which is present in the data set itself. Let's say you train on the first 70 samples, you test on the last 30 samples. Maybe the last 30 samples are the easiest to predict, right? So what you ideally want is to get your test accuracy scores across all of the samples, and this is where we do k-fold cross validation. What this does is, this is using k equal to 4. You split your data set into 4 parts. You generally end up using 3 parts for training and the 4th for testing, and you keep on cycling through the test set. The test set in this case is the last 1/4, the middle 1/4, the second 1/4, and the first 1/4. Right? So this way you would have trained on different subsets of the data, and you would have tested on different subsets of the data. Right? Is everyone clear to this point?
Once we have trained on fold one, then if the train set is going, we are using it as a test in fold two, that means is it wrong?
So the question is that let's look at fold 1. You've trained on, let's say, the first 25 samples, or first 75 samples, and you're predicting on the last 25. But in fold 2, you've trained on the first 50 and the last 25, and you're predicting on the middle 25, right? On the 50th to 75th sample. So the equation is, we have already seen 50th to 75th sample in fold 1, right? Isn't that wrong? What do you think? So these are all independently done. So what you do in fold 1 is independently done in fold 2, 3, and 4. For fold 1, you learn and classify on the train. You predict on the test. For fold 2, again, you look at only the train. You don't look at what happened in the previous one. Right?
So then it will be a final model.
Good question. So what do you think is the final model? What do you think is the final model that you'll use? Sorry? Which gives good accuracy on? Okay. Which gives a good accuracy on validation? Okay. Any other thoughts? Combination of all of these? So generally you don't look at a single model, you look at different. So this question is very important because if you have to put something in production, it's something to put results in a research paper, and it's totally different to put something in practice. In practice, you might look at a combination of all of these. Or sometimes you do something weird which which requires you to understand nested cross-validation, which I'll come to now. So we have discussed we do a k-fold cross-validation, but we've also discussed that we need to somehow split the train into train and validate, right? So for each of these train test pairs, how do you think we find the optimum set of hyperparameters? Let's say the depth of the train. What? So there are two different things. One, you divide the dataset into train and test. The other thing what you want to ensure is that you learn a model or you train a model in a way which gives the best test performance for that particular fold. So to simplify, just look at the first fold for now. Right? You want to get the best performance on the test set, right? How do you do that? You want to generalize, which means that you don't want to optimize on the train set. You want to optimize the parameters which gives and the hyperparameters which give you the best performance on a validation set. So only for looking at the first fold, you divide the train into train and validate, right? So what you've now done is you've nested and done some sort of cross-validation within the train itself, right? So again, you're doing the split within the train itself. Which validation set do you use? Do you use the last 10%? Do you use the first 10%? What do you think?
Again, cross-validation.
So you can again do cross-validation within the train set itself. You again divide it into different folds, and then you report the performance of the hyperparameter which gives the best performance across these different folds. So seems a little complicated, but if you try implementing it, I think it would be largely visible. Let's look at this diagram. This tells you the relationship between how are you splitting the data into train and test, right? But now you wanted to get the best performance on the test set, which means that you want to optimize not on the train set, because the train set optimization is complicated classifiers or regressors. So then you again need to split the train set into train and test, train and validate. So then can you split the whole train set into train, validate, train, validate, train, validate. So you're again doing k-fold cross-validation within the train set itself, right? So now you've so one other reason you want to do this is again the validation set could be biased. So subset of the train set could be very simple or very difficult. So you don't want to learn parameters, hyperparameters, only optimizing performance for that. So that is why you split even the train set across multiple of these folds. And this process is called nested cross-validation. The outer loop of cross-validation is for splitting train nest. The inner loop is for optimizing the parameters. Is that clear? Is that clear to everyone? And then how do you choose the best hyperparameter? So all of this is, think of it as done for one fold. All of this is done for the first row, right? The first row you have train and test. Now that train is divided into multiple folds again. Across these different folds, you'll have different accuracies for the different set of parameters and hyperparameters of validation sets. You end up choosing the hyperparameter which will give you the highest average validation accuracy, right? Average across the four different folds. For example, for the first fold in this, maybe depth equal to 2 works best. In this, maybe depth equal to 3 works best, something else. But then you look at the accuracy for depth equal to 2 here, 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 and here. And then you calculate the average across the folds. Right?
Why only accuracy? Why not choosing
So, anything. So just think of accuracy as one of you might know. Yeah, you could use it. That depends. So you ideally not want to learn. So his question is why not accuracy? Why not just accuracy? Why not precision and recall? Do you think you will learn a different classifier, a different set of hyperparameters, or different metrics? Probably not. You learn a single classifier, and then you have to choose a metric which is more important. So in the next lecture, we will discuss something known as ensemble learning or ensemble learning, where the idea is to combine different models. The questions are why do you want to combine different models? How can we reduce bias and variance, which are two things which we have seen? And is there any part of the error which is other than bias and variance? So we look at that also. And all of this should now be sufficient for our kind of